Okay, by now you've probably watched this video of the Tacoma Narrows Bridge collapse. It actually wiggled like that for an amazingly long amount of time, I think like hours. But this is what's called a standing wave, and we're going to get to what they are a little bit into this presentation. You can always look at the perfect sinusoidal function right here, up and down and back up. Right here, it looks like the bridge molecules, or that's part of the bridge, is not even moving. There's actually 1, 2, 3 sections are called nodes that are not moving. The antinodes are actually where you have the maximum movement of the medium. Medium is just what the wave is moving through. Waves carry energy. I probably should add momentum to that. They're divided up as to how they kind of move matter. Mechanical waves, that requires a medium. It's called mechanical for a reason. The big one's going to be sound. That's a type of mechanical wave. It's going to mean a lot to us because we're going to be making musical instruments. We will go to electromagnetic waves. It's light. And matter waves is the last topic of the course. Mechanical waves, they need a medium. You have to have something to move. The source of all waves is something vibrating, and mechanical waves are called mechanical because they physically move something. Water waves, water going through the ocean. The medium is the ocean water. Sound is the medium is the air. You know, everything can be a wave.
The beginning of modern warfare.
This is the property of a wave.
Red in tooth and claw.
By the end of 1915, Londoners had watched German airships rain death down on their city on 5 occasions with total impunity. Public outrage at the lack of civil defense forced the British government into action. To take out the Zeppelins, they brought in the latest anti-aircraft guns from France and positioned them around the capital. But the airships flew at night and were virtually impossible to see in the dark. Could they try to hear them coming? At Spurn Point on the Yorkshire coast, where the Zeppelins crossed the North Sea and entered England, a concrete structure called a sound mirror still stands. It was designed to
Basically
detect
a big
the
dish.
sound of the approaching airships. The sound mirror worked by amplifying the Zeppelin's engine noise. Sound waves hitting the concrete dish would be reflected and focused by the concave surface onto a single spot. This concentration of sound waves would increase the volume.
It's called wave superposition.
Using a horn on the end of a pole to pick up the sound, an operator would wait patiently night after night with his ears peeled. Once he detected the distinctive drone of Zeppelin engines, he would move the horn around until the sound was at its loudest. By tracing back along the line of his pole, he could locate the invisible airship in the night sky. With the help of acoustics engineer Dr. David Sharp, Hugh hopes to find out how effective this early warning system was.
With the stethoscopes on, the listener would listen out, and if they found that the sound was loudest in about this region here, then that would indicate that the aircraft was coming in from the direction that this is pointing, effectively.
Well, why don't we try an experiment?
Yeah, why not?
Hugh arranges for an aircraft to fly towards the concrete mirror. They set up 2 microphones. One picks up the ambient sound at the scene. The other, operated by Hugh, monitors the sound reflected by the mirror, just as the horn did during World War I. David monitors the output of each mic. Hugh's is in red. If the mirror works, Hugh's mic should pick up the plane first.
So by Hugh moving the microphone around, you can see when the pole's actually pointing towards the sound source, that's when the sound's coming up as its loudest on the microphone.
Although the plane is too far away to see, it's coming within range of the sound mirror.
I'm hearing it directly behind me.
Very clear peaks on the red.
I can't hear it without the headphones.
Hugh finds the area on the dish where the engine noise is loudest. His microphone pole points straight to a spot in the sky.
Well, I reckon it's out there.
You see those things on the sidelines sometimes at like a football game where they're pointing at a player and trying to pick up on what the person's playing, because by making it like parabolic dish, you can focus all those sound waves to a point and make them sound a lot louder. All right, there's 3 types of mechanical waves, and it's all based on how the medium is being moved. Transverse, longitudinal. There's really only 2 types because this is just like a combination of the top 2. So transverse wave, if you look at the bottom left, you could see the wave is going from left to right. Okay, if you were like a surfer on the wave, you'd be sitting right there and being pushed along by the wave. However, the particles are going at right angles to the direction that the wave is moving. This little red particle goes up and down and never travels along with the wave. Remember, a wave transfers energy and momentum, not physical particles. It helps me to remember it transverse is the wave particles moving perpendicular to the direction of the wave. Is that if you turn this big T upside down, it gives you that mathematical symbol for being perpendicular. Light is a transverse wave. And longitudinal ones, which is sound, the particles are moving parallel to the wave direction. So here you can see the wave is actually going, again, left to right, just following this compression, going left to right. But the particles themselves, they just go back and forth in the same direction that the wave is traveling in. So that gives you, like with sound, that gives you an area where the particles are compressed together, called condensation. I'm just going to say compression. And these areas where they're spread apart, called rarefaction. Yep, put them together, you get a surface wave with just a little bit of up and down motion, a little bit of left and right motion. But we're not really going to study that one. All right, the big electromagnetic wave we'll be talking about is light. Now, light, literally, microwaves and X-rays, they're all electromagnetic radiation. It's just light you can't see. We're only allowed to see, or able to see, a small bit of it. And when we do calculations, we're not going to use this number for the speed of light. We're just going to use 3 times 10 to the 8th. Makes life a lot easier. Matter waves we'll get at the end of the last topic of this school year. Not really important anymore. This is a simulation of the tsunami that happened off the coast of Sri Lanka. There was an earthquake out here, and I think a trough hit first, so that the ocean water was kind of sucked out, which was sad because people then started walking out into there, and then boom, the peak hit and came in. Well, what I really want you to see here is that anytime a wave hits a boundary, and a boundary is just a different medium to go through, we could say light going from air into water. Well, at the boundary where those 2 mediums meet, 4 things happen. They happen at different amounts depending on what the other medium is, but 4 things happen. Some of the light would get transmitted through the water. You know that because when you go into water, you can see things. Some of it gets absorbed. This is why the water's at the top of a lake is warmer than the water at the bottom, because it got absorbed and heated it up. Some gets reflected. You've seen light reflect off lakes. And diffraction is light's ability, or not light, I should say, a wave's ability to bend around an object. You can see I'm going to run this once, and you'll see the reflection. It comes out in this direction, hits India, boom, bounces backwards, hits Sri Lanka again, and that kind of just kept happening. It was really a bad one. And then I'm going to show you diffraction. That's wave's ability to bend around. So watch how it bends around the tip of India. You'd think it would just keep traveling straight in that direction, but instead it kind of bends around India. That's why if someone's out in the hallway talking, you could still hear them, because the sound wave can bend around, a door opening or something. So remember, these are the 4 things that happen when a wave hits a new medium. Some of the energy gets transmitted through, some gets absorbed, some reflected, and some diffracted. Another video, the same thing. This is an actual tsunami, and man, there's some power associated with this. This is a wave that just doesn't stop coming, and it's pushing everything with it. Trucks and homes and everything. There's a house right there moving. In a minute, you're going to see an actual boat got pulled out from the sea and goes right underneath that overpass. There he goes. I'm going to kind of jump to the end on this one. Oh yeah, actually, I like this one. Everybody's bugging out because here comes the wave, right? Some people aren't paying attention. This guy in a white car comes in. Whoop, the wave coming. Then the guy in the black car, he's like, I'm on a cell phone. Ooh, this is why you got to make a K-turn to pass your test. You go. I'm going to skip that one because I'm not going to use it much. Every wave I refer to is going to be a periodic wave. I'm just going to say wave, okay? And that means it's going to be regular repeating. That means it's going to be doing exactly the same thing on the way up as the way down, just different directions. And the length from like a peak to a peak is going to be the same as the length from a trough to a trough. It's just regular repeating identical waves. Crest is the tippy top, and the trough is the bottom. This here is the line of equilibrium. Probably saw this from math class. Amplitude is the distance from the line of equilibrium up to the top of a peak, because we're doing regular repeating waves. That would also be the same as the distance from the line of equilibrium to the bottom of a trough, because we're using these particular waves. They're not all like that, but the ones we use will be. Period, we've seen this before. It's a time for one full cycle to happen. So that means this wave has to go all the way up, turn around all the way down back to equilibrium. Now it's heading the opposite way it was heading over here. So you've got to go all the way down and right back up to same point, same direction you were heading. So that is the time for one cycle to happen. Frequency is the inverse of that. So if I flip it over, instead of having time per one cycle, it's cycles per 1 second. Frequency, when we talk about sound, is going to dictate pitch. However, frequency, when we talk about light, that actually dictates color. So it says find the frequency of a wave with a period of 0.5 seconds. Well, 1/0.5 is 2 cycles per second. Wavelength is literally what it says, the length of a wave. That is the Greek letter lambda. And that is in a formula, that's wavelength. And because we're using regular repeating waves, it would be the distance between a peak to the very next peak, which will be identical from a trough to the very next trough, or from the beginning of like the sine wave at equilibrium all the way up, all the way down, back to where you started. That distance would be the same as that distance or that distance. We have two speakers. If they're in phase, that means they're both producing a sound that has a peak hit a peak, a trough hit a trough. So if each one of these were 1 centimeter high, 1 centimeter high, 1 centimeter deep, 1 centimeter deep, it would produce one single sound, and that would be 2 centimeters high and 2 centimeters deep. It's called wave superposition. It's called constructive superposition when they add up nicely like this. However, if they're out of phase, which I'm going to show you in the next video, that's called destructive superposition. That's where they're lined up so that the peak of one hits the trough of the other one, and they start to cancel each other out.
Here again on the Abyss Headphones channel, and today I want to talk about phase. Now, right here I have two speakers, and they're going to play a little bit of an unpleasant sound for a moment. Now, I know that's not great, but watch what happens as I move this speaker forward. You'll notice as I move the speaker forward, it's getting quieter and quieter, but if I keep moving it past this point, it starts to get louder again. Now, why is that? Well, that is because of something called phase. That's what we're going to talk about today. So audio works in cycles and in waves. Now, it sounds a little bit weird at first, but imagine this. The sound coming out of this speaker is a wave of pressure moving up and down or forward and backwards through the air. And that is what is reached and interpreted by our ears. Phase is essentially how far through its cycle a wave is before it repeats. So 360 degrees would be a full rotation. Now, if that doesn't make any sense, imagine this. A rotation would be a wave moving up and then down and then back to neutral. That's one full rotation before it starts again. If you get these waves happening a whole lot really fast, it's going to make a higher pitched sound. If you have them happening very slowly, it's going to make a lower sound. Now, if you were to take two sounds that were in phase, saying two sounds that are lined up, they're at the same point with each other as they're moving through the cycle, they're going to amplify one another. However, if there's two sounds that are out of phase, meaning that they are not aligned, they're going to work against one another. Whereas this may be moving up, this will be moving down.
180 degrees
And
out of
as they
phase.
cross paths, they cancel one another out. Now, I couldn't cancel these two speakers out perfectly because, well, we're not in a treated room, and you have to deal with reflections off the table and other things like that, but it definitely made a difference in the volume. Now, phase is affected by placement, but it's also affected by signal. Say if I was to reverse the positive and negative on the speaker in one ear, or to this speaker while it's sitting still, or even the analog signal going to the amplifier on one of the channels, that would change the phase in one speaker and change the output sound.
We're not going to talk about that this year. We're making string instruments, and this is basically what a string is going to do on a guitar or a violin or a banjo, whatever. You're going to have two fixed ends, and it's going to wiggle like this. You're actually producing a standing wave, kind of like the Tacoma Narrows Bridge. When you pluck the guitar string, you pull it up, you send a wave from one end to the other one, and then when you get to the end, because it's much more difficult for the wave to get past that, it's a new medium because it's tied down there, most of it, the energy is going to get reflected, and when it gets reflected, it heads back the other way 180 degrees out of phase. So sometimes those two waves going in equal and opposite directions are amplifying each other. They're doing constructive superposition, and sometimes they're doing the opposite. They're doing destructive superposition. So the next slide kind of shows you it. It shows you I think it's a green wave going to the right, and the reflected one I think is the magenta one going to the left. Yellow is what they look like to you, because right now you've got two lined up where the peak hits a peak. Constructive superposition gives you a wave twice as high as these guys, and when you get a peak and a trough, you'll be in the middle. Watch it. Right where that's destructive, come back together for constructive, and they destructive, and they come back together for constructive. That's what's actually going on inside of the guitar string. That was the first harmonic, or what's called the fundamental frequency. It's the smallest possible wave function you can actually get in anything. We're going to refer to guitar strings or strings. It's actually half a wave, right? If you look at this standing wave, that'd be all the way up, all the way down, and the other part of the wave would be on the other side. So it's half of a wavelength is our fundamental frequency on our first harmonic. There's a node here, and there's a node here. That's the area of no motion. Antinode in the middle, that's the area of maximum displacement from equilibrium. And this is a half a wave. Second harmonic would be one full wave. You can see all the way up, all the way down, perfect sinusoidal function, right? Node here, node here, node here. So 3 nodes, 2 antinodes. And again, just like the other ones, created by the green and magenta waves heading in opposite directions. Sometimes they're superimposing constructively, sometimes destructively, which kind of kills the wave there, but then back to that. So you're seeing the yellow wave. What's actually happening is what the green and cyan or magenta wave does. I guess if we put green together with magenta, you get yellow. This is one of the few formulas we're going to be using in waves. Usually like this, though. Speed of a wave is dictated by, 1, the medium it's in. So if you need the speed of sound in air, you go look it up on a reference sheet. That's usually what you get. So if you multiply the frequency of the wave times the wavelength, you're going to get a unit of meters per second, and that is velocity. But keep in mind, dictated by the medium it's in. We talked about this a little bit already. When peak hits peak, you get constructive interference. They're additive, the waves, and they just go on their merry way. When a peak hits a trough, you get destructive. Right there, it goes dead for a second, and then 2 waves just keep heading the way they were going. If you had a body of water and you kept dropping 2 stones in it at regular repeating patterns, you would get regular repeating waves going out. At some point, a peak from this wave is going to hit a peak from that wave, and they're going to interfere constructively and add up to one big wave. There's also points where you're going to get a peak from this one hitting a trough from that one, and then you get destructive superposition where it kind of goes flat. It looks like this. Like if this was us dropping something into the water, you would see propagating out. You'd see these peaks where 2 peaks lined up. Then you're going to get these sections where a peak lined up with a trough. Troughs lining up. You're going to get a location where they're destructive, constructive, and so on and so forth. And if this was light, you would actually see on a screen over here, you would see bright spot, 0 light, darkness, bright spot, 0 light, darkness, darkness. That's an interference pattern. So that's like the telltale sign something is a wave. If you can do this and it interferes with the other wave, and you get this interference pattern, that has to be a wave. You'll see why I'm harping on this in a minute. Yep, just led people to believe that light travels like a wave. Used to think it was particles. Of course, you have a formula for it, but I'm not really going to get into that this year. I'm going to go with the musical instruments. You can calculate everything about the wavelength of it and whatnot. So we're skipping this. This is an electromagnetic spectrum. Again, it's all electromagnetic waves. We just get to see this tiny little bit of it that we call the Roy G. Biv of the rainbow. Go a little bit to the left of red, you get a lower frequency light. It's going to be called infrared. You can't hear it. You can't see it. You can feel it though. This is like heat coming off of a fire. That's infrared radiation. Some animals I think can see infrared. They can hunt at night like that. Then you go up to higher frequency stuff, and you go outside the violet. You get to the ultraviolet stuff. It's that high energy light. It's the kind of stuff that can penetrate your skin, cause skin cancer. Up here, again, you can't see it. All you see is in between these 2 lines, and it's blown apart for this. So, I think I mentioned sound frequencies dictated by. Loud. I'm screwing this up. When it comes to sound, frequency dictates pitch. So that's going to be used when you make your instrument. But when it comes to light, frequency dictates color. That's how your eye sees light. So when we were talking about why it's important for the interference pattern thing, take a look at this.
And here we are.
Well, it's
the
cartoon,
granddaddy
but
of
that
all
is Professor
quantum weirdness.
Wolf
The
from
infamous
California.
double slit experiment.
Fred Allen Wolf.
To understand this experiment, we first need to see how particles, or little balls of matter, act. if we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
That's some crazy stuff we'll be doing at the end of the course.